So I'll just tell you a little bit about myself. I'm the Coherence product manager at Oracle, and I was formerly on the Coherence product development team, and prior to that on a outbound engineering team. I've been with Oracle since 2005. I came from a company called IQ Navigator where I was chief architect. And during those years, I was also on the technical advisory board of Raleigh Software Development Corporation. And I've enjoyed contributing to software architecture literature over the years. I'm kind of embarrassed to admit it, but way back in the day, I committed to this book called EJB Design Patterns by Floyd Miranescu, and a few more recent books since. So that's a little bit about me. And let me tell you a little bit about the topics we'll cover today. I'll just give a little introduction to domain-driven design in case people don't know what it is. Same thing for in-memory data grids. I'll just give the briefest overview of in-memory data grids. And then we'll get into the real meat, the patterns of using domain-driven design with in-memory data grids. And I'll talk a little bit about some cool new stuff that's happening in this space. And then finally, we'll have some Q&A at the end. So I think, Venkat, can you tell me, I've got 50 minutes, including Q&A time, correct? I think that's true.
Right. Yep, that's right, Randy.
All right, thank you. Okay, so let's dive right in. So what is domain-driven design? Well, it is the architectural style at the core of the object-oriented tradition. It features an object model of the problem domain you're working in. The application that you're developing is addressing, some problem, and you model it with objects. So this is the architectural style that object persistence technologies like object relational mapping tools and object-oriented database management systems have always been designed to support. The presumption is you're going to be mapping objects to a database, or you're going to be storing objects directly in an object database. Interestingly, over time, the representation of object state has changed. When I really started getting into object-oriented programming in the late 1980s in Smalltalk, of course, we had object-oriented programming languages, and they had objects, and we still do, of course. But when SOA came along, 20 years ago or so, we started representing object state in XML, and nowadays with HTML5 and NoSQL and microservices, we're representing object state in JSON. And this kind of opens a question of, well, where is behavior implemented? Because in theory, an object is state and behavior together. But and there's a whole literature about domain-driven design. I put some of the book covers here. The book that kind of started it all, gave it a name, was Eric Evans' book in 2003. And then Jimmy Nielsen came along a few years later with a book, and Von Vernon, I think this is a 2016 book, Implementing Domain-Driven Design. But if you look back at some of the older literature, this is a 1998 book by Martin Fowler, where he's basically documented reusable object models for different problem domains. And there was more of a RDBMS-oriented one of the same by David Hay. And this book, Data and Reality, is actually a 1978 book, which has all the familiar themes. So this is a pretty old tradition in software development, and it's very popular now. If you look, there are conferences dedicated to domain-driven design, and there's a book about how to do it in every possible language, PHP, .NET, etc. So that's domain-driven design. Let's talk about the concepts that are in it. So in domain-driven design, you have domain objects, which are different than data transfer objects. They're not intended to transfer data from one place to another. They're intended to model something and implement behavior that is logic that's required by applications. And you have domain models that are made up of domain objects or domain object classes. And there are different kinds of domain objects. You have entities that are distinguished by identifier, and you have value objects that are distinguished by state. And I'll point out a couple examples in a minute. You have the notion of aggregates, which are groups of related domain objects that in which invariants, so to speak, are maintained in a transaction. So take a simple example. If you have an account with some transactions in it and you're keeping a balance in the account object and you add a transaction, when that when that commits, the balance needs to be right. So that's an invariant. And of course, aggregates have a root object. In that last example, it was the account. Obviously, you have relationships between objects. They can be association or have more of an ownership or composition semantic. And then you have what are called repositories, which represent, the collection of all entities of some type, slightly different than data access object. So this is a domain model, a UML class diagram of a domain model from a job I did at an airline company quite a while ago. And, back in the days when we used to fly and travel before the pandemic, LOL. So in this model, a good example, well, so a flight is an entity. It has a number and a date, which make up its identifier, a carrier. And a pilot trip is an entity. A good example of a value object would be this time tuple. In the air travel industry, a flight has a time when it pushed back from the gate, when it left the runway, when it landed on the runway and got into the gate. So that we modeled that as a time tuple. It's a value object, doesn't have an identifier. So aggregates in this model, a pilot trip is an aggregate. So one pilot taking a trip for his company, a trip is comprised of duty periods, and duty periods are comprised of segments. And these objects all group together in an aggregate, and the pilot trip is the root of that aggregate. Another example is a flight. A flight consists of one or more actual flight legs, each of which has an estimated and an actual time tuple. So a flight is an aggregate. And then there's association relationships between pilots and flights. Obviously, there's composition relationships within those aggregates. So those are the concepts in domain-driven design. And when you have an application that's implemented with the domain-driven design architectural style, these applications tend to have certain runtime characteristics. Historically, especially with object relational mapping tools, domain-driven design causes large, highly interconnected object graphs to hydrate into the memory of a process, like an application server, like, let's say a J2EF server with Hibernate. You end up, as you retrieve objects from the database, they end up filling up the JVM heap, and they're all pointing to each other. They reference each other by pointer references through fields of classes. And there's also a phenomenon where a collection typed field may accumulate many elements over the lifetime of an application, a business application, or even an application server instance. We see this with Coherence customers where there may be collections that have tens of thousands of elements, and that causes some unique challenges. So these object graphs that grow in process memory, they have a tendency to hinder object movement between processes. Originally, between rich clients and application servers, this is why DTOs were created, and also between middle tiers and persistent stores. If you try to serialize a large object graph, you end up with a byte stream that might be a megabyte big or something. And these object graphs also tend to hinder movement between clustered cache servers and an in-memory data grid. Another characteristic of DDD applications at runtime is that, quote unquote, application level transactions, they usually involve multiple entities, and they may even involve multiple aggregates. This tends to depend on user interface design or else API design. And so you need to be able to atomically mutate many objects at a time, which may be in separate aggregates depending on UI design. And that may require you to need transaction isolation in the domain layer. ORMs solve this in different ways. Object databases solve this in different ways, but in-memory data grids have the same challenge. If you have multiple user sessions that are that want to write to the same object graph, how do you isolate those edits from each other and commit them in sort of ACID ways, if you will. All right, so those are some runtime characteristics of domain-driven design applications. And now let's talk a little bit about in-memory data grids. So what is an in-memory data grid? It's actually, there does not seem to be a good standard definition out there. There's not one on Wikipedia. You know, if you Google in-memory data grid, the top hits are going to be IMDG vendors giving their own definition, which is what I'm doing here too. So I consider an in-memory data grid to be clustered data management and grid computing software. In-memory data grids are intended to improve the performance and scalability of enterprise applications. That's what they do. They are deployed within very high scale, very mission critical applications, and their job is to provide fast access to data, allow the applications to scale, protect back-end databases from load, and generally ensure reliable access to data. They tend to implement a key value data model, typically a map interface in an in-memory data grid. You could also consider that they implement a document data model. You know, you might be storing, you know, a JSON document or an XML document in some key. And there's plenty of examples of that. And in-memory data grids are distinguished from simpler distributed caching platforms by incorporating powerful features. For example, persistence. I think most in-memory data grids on the market now have persistence, and they're sufficiently reliable that they can be systems of record. You don't have to cache in front of a backing relational database if you don't want to. You can literally use an in-memory data grid as a system of record. They have pretty much by definition the ability to query the data by other than key. So you can say, give me all the key value pairs where some attribute of the value equals some constant. And similarly, you can aggregate over the contents in the same way. And these tend to be distributed in parallel algorithms in an in-memory data grid. They tend to contain in-place grid computing features. And what I mean by in-place is that you ship the function to the data, and the function runs, you know, in the servers where the data lives. Again, in a parallel distributed fashion. And that's probably the defining characteristic of an in-memory data grid, very powerful feature. And they tend to have some kind of transaction support capabilities. They also have eventing, a very rich event model, so you can listen to events and implement event-driven architectures. Some of them have a messaging system built in. Coherence does, with all the familiar concepts of subscriptions and topics and so on. They may have multi-site data federation for geographic proximity or disaster recovery. And they may have a change data capture mechanism. I saw another talk at the In-Memory Computing Summit about this, I think from Hazelcast. Coherence has it as well. Now, the distinction between an in-memory data grid and NoSQL technology has grown fuzzy over the years. In the earlier years of in-memory data grids, when they didn't tend to have persistence, the distinction was pretty clear. NoSQL technologies were able to persist data on disk beyond the life of a process. Well, now in-memory data grids have persistence too, and so I tend to view them as they are NoSQL databases. They generally don't store the same volume of data, certainly not petabytes, maybe single-digit terabytes is what we're seeing, and they have more capabilities than NoSQL databases. It's that list of powerful features that I just went through. So that's what in-memory data grids are as a technology category. And I'll show you a little history timeline here. And I know that I've omitted a couple. For example, Scale Out, who's at the conference, is not represented here, nor is Gigaspaces. And there are others that have been in the space that have kind of fallen away, like IBM WebSphere Extreme Scale, or maybe to a lesser extent TIBCO Active Spaces. But from our point of view, Coherence was the first. Coherence came to market in late 2001. The company was founded in 2000. The company was Tangasol. Oracle acquired it in 2007. Gemfire is about as old as Coherence. I think early 2000s timeframe, certainly by 2005. It's been through a series of mergers and acquisitions and divestitures, and it's back with VMware now. Hazelcast came out in 2008, GridGain in 2010 or so. And what's interesting is these commercial products spun off open source implementations in sort of an open core model. I think GridGain, well, Hazelcast had an open source and a commercial offering from the beginning. GridGain spun off Apache Ignite in 2014, and Gemfire spun off Geode in 2015. And we spun off Coherence Community Edition just earlier this year, which, as you can imagine, is a pretty big deal for Oracle to create an open source edition of a formerly commercial product. So that's a little bit of the landscape. And I noticed at this conference that there were, a number of sort of product specific sessions. So I just wanted to put in one or two slides to talk about Coherence. This is the Oracle template now. So just a quick feature summary on Coherence. One of the things that we have that you don't get in, for example, Redis, is fault tolerant automatic sharding. Your application doesn't need to know which cache server holds the data. We decide based on a modulus function of the serialized key and a partition ownership map, and we create one backup or replica automatically. We have polyglot and REST client interfaces. We have all the usual in-memory data grid features. We have this hot cache change data thing that I mentioned, and federation and messaging. And we support Docker since 2016. We have our own Kubernetes operator. And in our most recent release, we implemented support for open tracing. So our spans can fit into larger scope spans and so on. And just a word on Coherence Community Edition. We launched in June 2020. This is a free and open source edition of Coherence. It is the core of the commercial editions. It's an open core model now. It's hosted on GitHub under UPL, and we publish our artifacts to Maven Central and Docker images on GitHub. So Coherence Community Edition entitles a subset of Enterprise Edition features. The premium features and first-class product support still require commercial license. So one of the reasons that we're doing this is so that we can make twice a year interim releases to give early access to features that are coming in the next commercial releases. So for example, when we launched in June, we released an integration with Helidon microprofile, which is a microservices framework. And we released a new gRPC-based proxy server and a Java client for it. And since then, we've released a JavaScript client for it. So you can now have native JavaScript access to Coherence. This is part of a platform for cloud native microservices applications. And here's the links to the new website for Coherence Community Edition. So that's just two slides on Coherence. And now let's really get into the meat of this session. How do you implement domain-driven design within memory data grids? And there are some subtopics. How do you take a domain model and map it to a set of maps, since map is kind of the primary abstraction that you deal with in an in-memory data grid? How do you handle relationships between domain objects? Really tricky thing. How do you implement transactions, especially that modify multiple entities or multiple aggregates? And then I just have a list of sort of general domain model caching patterns or use cases. So this is a question that's as old as the technology itself. These are a couple photos from a summit meeting I attended in 2012 in Portland, Maine, that I actually helped organize with Eric Evans and Vaughn Vernon. So we had the sort of open conference model where we put stickies, and there was a group that emerged about DDD and NoSQL. People in the picture here, this is Eric Evans. This is Von Vernon, this is Jimmy Nielsen, me, Cameron Purdy, who was the primary architect of Coherence, Martin Fowler back there, etc. So the point is, this problem is not new. So when you go to store a domain model in an in-memory data grid, the first thing that you have to be aware of is that in-memory data grids have a unique programming model. You're dealing with a map interface and however many different maps you want. It's not like object relational mapping where you take an entity manager and tell it to find something, and then you start navigating an object graph from there. Also, in-memory data grids give you a new tier of architecture between app servers or microservice containers and backing databases, and that new tier of architecture can run behavior for you. It can run logic with the in-place processing stuff. So it's a completely different programming model or architectural model. And the most important decision you have to make is you have to choose a pattern for mapping your model onto a set of maps in the in-memory data grid. And there's three broad patterns, which I'll cover in more detail on the next slide. You can have a map per entity type, a map per aggregate route type, if you remember the definition of aggregate route, like a pilot trip or a flight. Or if you're working in a problem domain that has significant state models for objects, and an obvious one is orders, you can have a map per object state. And then once you have that sort of pretty big decision made, and you can use a mix of these, by the way, then you have to figure out how you're going to implement inter-object references in your domain model, which is kind of that decision kind of depends on the mapping pattern you choose. So as you know, normally with object relational mapping, objects just kind of point to each other by pointer reference, maybe with some kind of indirection or proxy, so that you can do lazy loading and so on. Well, with an in-memory data grid, you may have to let objects refer to each other by some kind of identifier, and then query for the related object using the identifier instead of just navigating a pointer. And of course, you have to implement keys for the maps, which comes pretty naturally for entities. Since entities have identifiers, the identifiers tend to be the map keys. You have to implement serializability, because with an in-memory data grid, we're moving data across the wire, so you have to make sure that your domain objects are serializable somehow, which normally you don't have to do with like an ORM. And then you may want to implement repositories to sort of encapsulate the IMDG API so that your application code is just talking to repositories and saying, find me domain objects with these criteria, or insert this new one or remove this one, with the sort of CRUD API that you get on a repository. And this will protect, if you want to switch IMDGs or persistence technologies in general sometime in the future, you can just have a different implementation of the repository interface, and it protects your higher layer application code from variation in your persistence technology, although there's leakage here. It's not a perfect abstraction. So for example, if you call read on a repository, are you getting back a shared object or a transactional isolate? That's one of the leaks. Okay, so that's kind of the high level landscape of storing domain models in an in-memory data grid. Here's those three major mapping patterns and the pros and cons of each. Map per entity type is a well-known precedent from the object relational mapping world. If you look at Hibernate or TopLink, they all have a map per entity type. I wrote the Hibernate second level cache implementation for Coherence, and so I've seen what that looks like from a SPI implementer's perspective. This is the simplest mapping pattern. It's very uniform. It's very predictable, but if you implement this pattern, it means that navigating object graphs requires repeated cache access, because every time one entity refers to another one, you have to go access that other entity's cache to get the related object. And it also means that transaction handling is more difficult because you have, let's say you have an application level transaction that wants to modify a couple dozen entities. They may be all in different caches, and so now you have to coordinate an atomic commit amongst several different caches at best, and that's challenging. Also, with this pattern and map by aggregate root type, if you want to do a query for all the objects, if you want to get all the objects that are in a certain state, you have to query for it. So I think for most applications, the recommended pattern would be you start with a map per aggregate root type. So you identify your aggregates in your domain model. This fits really well with the domain-driven design notion of aggregates. You can serialize all the related objects in the aggregate together and store them as one value and a key value pair. This gives you really efficient data access. You want to retrieve an order at a time with all of its line items and maybe some quantities and information about the product order. You get it all back in one serialized blob. And it's also really easy to transact atomically because it's a single cache entry. So if you want to add a line item to an order, you just put the whole order, the whole updated order back into its cache, and you're done. The cons of this, it's kind of non-uniform because the aggregates really depend on your domain model. It's hard to make a framework for this pattern, and it leads to kind of bespoke code about, your application code knows which repositories it has to talk to for which aggregates and so on. And again, it has the same query requirement for different states. So the other one, and this is much less used, but you can have a map per object state. So think about a typical, e-commerce application with a shopping cart with orders. You have new orders that haven't even been paid for yet. Then they go through payment, and now they're in a paid state, but they're unfilled. And then once they're filled, you're kind of done processing. So order has a pretty significant state model. You may want to have a cache of all orders in the new state, cache of all orders in the paid and filled states. And then if you're doing order fulfillment, you can just grab all the ones out of the paid state, fill them and move them into the filled state, which means you're moving them between caches. But it's pretty efficient for accessing all the objects in a certain state. So those are three major patterns for mapping domain models to maps that you have in in-memory data grids. Let's talk about relationships now, because this is tricky. So let's say you have multiple cardinality relationships in your domain model. Well, order and line items, we can stick with that. So you have a choice. You can either store all the line items with the order, serialized together as one blob, or you could have a separate cache for orders and a separate cache for line items, which doesn't really make a lot of sense, but go with it for a second. And then, so when you have that, you can let the line items hold their order ID. And then when you want to get all the line items for an order, you have to query the line item cache for all line items whose order is this ID. That's a perfectly acceptable way of doing things. Another alternative is you can let the order hold a collection of identifiers of line items. And then if you have a reference to the order, you ask it for all its line item identifiers. And then you can do like a get all call on the line item cache and get all the line items back all at once. And get all tends to be more efficient than a query. Queries require indexing and all that stuff. So it's just one call, and you may need in these cases to manipulate collections without deserializing. This is sort of a tale from the trenches, a pain point, scar tissue. If you have one of these collections that can have tens of thousands of elements in it, and there's some kind of business process going on where you're adding multiple new elements at the same time, you can potentially deserialize and reserialize that collection, that large collection, however many times you're adding a new thing to it. So we've had to figure out ways to work around this or solve this for some of our customers, and it's one of the tricky parts of these multiple cardinality relationships. And a final alternative, which I think makes sense in a lot of cases, is you can actually have a separate cache for relationship objects, kind of like an association table in a relational database schema. Then you can just query that cache for all the relationships involving one object, and once you have them all, you can query some other cache for all of the related objects with a get all call. So it's 2 round trips. Okay, so that's a little bit about relationships. And now let's talk about transactions. We've already sort of alluded to these single entry transactions where it's just one key value pair. It's one value that you're modifying, and that value may be an aggregate. And maybe you're modifying multiple things inside that aggregate and putting it, serializing it all together and putting it back as one value under one key. That's certainly a good and efficient use case. But I wonder whether applications designs tend to get skewed towards that because it is the easiest and the most efficient, when maybe a better user interface design would allow a user to modify multiple aggregates at once. So you end up skewing things to avoid that because it's technologically challenging. Well, we have a feature in Coherence that we call partition level transactions, whereby we can atomically modify multiple key value pairs where the values may be separate aggregates under certain restrictions. Every key value pair involved has to be part of the same partition that we call it in Coherence. So it's in the same cache server process, and you have to have configured data affinity on this cache. But that's sort of an in-between of a single entry transaction versus a full-blown 2-phase XA JTA distributed transaction that is very efficient in Coherence. Then the final option here is this Coherence transaction framework, we call it, in which caches act as J2EE connector architecture resources, and they can participate in JTA distributed transactions. We generally don't encourage people to use this because, of course, you get the performance characteristics of 2-phase commit. It's a really heavyweight thing to do. So in general, I found this to be the hardest problem in implementing domain-driven design with in-memory data grids. Is you have to think very carefully about what are the transactions that I need against my data grid, and what's the best way to implement those transactions, and that may influence your choice of how to map your domain model onto a set of maps. So that's a little bit about transactions. Now, here are some sort of higher level domain object caching use cases, or you could call them patterns, I think, if you want to. The most obvious one that really shows the benefit of in-memory data grids or distributed caching platforms is just read caching. There have been a lot of users of Coherence in e-commerce and retail over the years. An example, we have a company in Spain called El Corte Inglés. They're the biggest department store in Spain, and they tend to cache their entire product catalog. Everything they sell in their department stores is held in Coherence, and they tend to cache inventory levels. And so their applications, their website is basically reading from Coherence instead of reading from backends, and that's to offload the backends. So read caching is a very common use case. Another one is write buffering. This one's a little more interesting. I've seen multiple cases where a high-scale application that's using an in-memory data grid can exceed the write capacity of even like an Oracle RAC database. And so people will put an in-memory data grid in between the app and the database so that they can buffer and coalesce the writes. So we can write to the database asynchronously, and in that interval between writes, we can coalesce multiple updates to the same cache entry. And we can also batch the writes so it's not one at a time. And so that's a write buffering use case. It's relatively rare, but when you need it, you need it. We have quite a few examples of event processing use cases. One of the Coherence users that's spoken publicly a lot about what they've done is Union Pacific Railroad. They have a really cool logistics system based on microservices, and they also have, in their big enterprise, they have sensors on their track network, and they know when trains go by, and they know when positions of things are updated, positions of locomotives and freight cars and shipments and so on. So when those position updates come into the logistics system, it kicks off event processing. And there's plenty of other examples out there in IoT space, for example, toll roads, meter reading, etc. Grid computing is a general use case that is actually very popular, obviously within memory data grids, and probably the canonical example of this is risk analytics in financial services industry. We've had at least a half a dozen large multinational banks implement risk engines on top of Coherence because the processing is so complex that being able to do it where the data lives instead of retrieving the data and putting it back allows for order of magnitude decreases in execution time. So companies can now do intraday risk calculations instead of overnight batch runs and so on. Synchronized projection is a little bit obscure, but if you have a sort of a legacy schema and yet you have a new app that wants a new domain model, and you have to keep the two in sync, so you have different projections of a domain model, and when state mutations happen, you can project the state mutations over both different models. Union Pacific actually has a little bit of that. Key mapping is pretty obvious one. You have a cache whose keys are secondary keys of objects and whose values are primary keys of objects, and so you can translate from secondary keys to primary keys and do 2 round trips for a lookup instead of a query. And also, we've had precedent for computation result caching. For example, a company using Hadoop for big, heavy computations, and then they store the results in Coherence. So those are some sort of big, broad use cases for caching domain models in memory data grids. So now let me talk a little bit about what I just called cool new stuff, and I have to confess to a little bit of a lie here. Hot cache is actually not that new. We introduced it in 2013 using Golden Gate. This is the change data capture feature. I actually did a Java 1 talk on this a few years back with a person from TELUS, which is a mobile operator in Canada, and we talked about the patterns for transforming a legacy schema into a new canonical domain model. Well, what this is all about is if you want to use caching in some application, but you're caching data from a shared like legacy database that other applications are writing to, you have to solve this stale cache problem. You know, as soon as you put a cache underneath an application, that cache can become stale because the database is being written out from under it. So what this change data capture idea does, and Coherence is not the only one that has it. You have some way of listening to the database transactions. For us, we use Golden Gate, and Golden Gate has a Java adapter. So we can get essentially a callback every time there's a database transaction that affects a cached object, and we map, we use JPA, so we map tables to entity types to caches, and then we map, you know, the table's primary key to a cache key, an entity ID. And so when we see that there's a write that's happened in a database, we go find the right object in the right cache and we apply the update. And this is in an event-driven kind of fashion, pretty real time. We see lags of maybe a few seconds between database commit and cache update. And this can be scaled out by parallelization. I think this is an old slide, but we've tested this to about 20,000 writes a second. So this is a kind of a cool addition to in-memory data grids in the last 5 to 7 years, where you can now cache in front of volatile databases and keep the cache refreshed, keep the cache in sync, which is pretty cool. The next thing that we're doing, and I know some other in-memory data grids are doing this too, is we're putting a GraphQL interface on the front of the in-memory data grid. So if you're not familiar with GraphQL, it's basically a query language for calling APIs. And what's really exciting about this for an in-memory data grid is it allows you to do object graph navigation when the objects are stored in different maps. So it kind of addresses this problem of, reference by identifier instead of reference by pointer. You still do the reference by identifier, but your GraphQL server can be in the cluster and can navigate the relationships without your GraphQL client really knowing what's going on behind the scenes. So this is really exciting to me as an old domain-driven design guy. It'll make in-memory data grids more seamless to use for domain-driven design-based applications. So we'll be releasing our GraphQL implementation in one of the next couple of releases of Coherence Community Edition, and then obviously the following Coherence Commercial Edition. And I think that is the end of my content, but let me just summarize. Domain-driven design is a good architectural style. It's very proven, it's very popular, I think even growing in popularity. If you Google for domain-driven design conferences, there's one on every continent. It used to be there would just be a domain-driven design track in a bigger conference. Now there's entire conferences devoted to it. There's probably close to 24 books on it. And of course, in-memory data grids are awesome technology too. So using the two of them together makes a lot of sense in the context of really high scale enterprise applications. Domain-driven design is a good way to organize logic, and in-memory data grids are a good way to make these kind of applications scale. So I recommend, to practitioners, if you're building a enterprise application, please use domain-driven design and please use an in-memory data grid to achieve your performance and scalability goals. And with that, I think I'm done with the content, and I've got about, I think, 7 minutes left here to answer any questions people may have. I'll look at the GoToWebinar chat function, I guess, or we do it interactively over microphones, Venkat?
Yeah. Hey, everyone. If you have any questions for Randy, just go ahead and post it on the questions box. If you want to just speak up, just just send me a quick note and I'll unmute your line. So Randy, if someone wants to get started with domain-driven design and IMDGs, what is your sort of like favorite place to sort of learn this, right? How do you?
That's a good question. So a couple resources that we have on the coherence.community site, there's an example to-do list application. So it's got just a couple of simple domain objects, like I think seriously there's a domain object class called to-do list, and there's one called task or something with the obvious one-to-many relationship. And that example on that website shows how to build and deploy it with Maven, run it with Kubernetes, and I forget what the user interface for it is like. It might be command line, or there might be some simple web interface for it. So that's like a quick start. If you want to go in more depth, there's a book called Oracle Coherence 3.5. Obviously the version is old, but the content in there is all still very relevant, and it's still very DDD oriented. And I actually think Von Vernon, in his Implementing Domain-Driven Design book, I think he has a chapter on doing domain-driven design within memory data grids. So look for those things. Coherence.community, Coherence 3.5 by Pact Publishing, and Implementing Domain-Driven Design by Von Vernon. And thanks everyone for attending. Have a good rest of your week.